So Paul showed us how we can take the little divots of the universe and magnify them through gravity to make structures that are really dense and look like the stars and galaxies of today. So as the universe fades away from the time of the cosmic microwave background into the dark ages, we can have computers and see how gravity works. So Paul, how long does it take approximately before the first stars and galaxies can be formed out of the cosmic microwave background?
Well, it's a bit tricky to calculate because we have to know a lot about what the fluctuations were to begin with, and we don't know where they came from. But there's some reasonable assumptions of that based on what we can see of the microwave background. We're talking 100 million years, plus or minus quite a bit.
So we don't really know it that well, and whenever the theory is not very good, I always think we should just go out and look. But the problem is we need to figure out how to go look for these really, really early stars, and we need to have a signature to find them.
Yes, I mean, it's a great quest for modern astronomy to see the first stars. And we're going to talk about several different ways in which we approach this problem as we go through this lesson. One approach would just be to have a really, really good telescope and look for them directly. We can't do that at the moment, but we might be able to in the future, so we'll come back to that. A second approach is to look at the relics of these things left over today. So maybe even though we can't see them, the burnt out remains of these first stars might still be around. But we're going to start off by a third and very sneaky way to do this, which is to look not for the first stars themselves, but for their effect on the gas around them. Because our N-body simulations predict, yes, you formed the first stars, but there should still be at least tenuous gas everywhere else.
All right, so let's look at what we're going to use as a signature. Hydrogen would be a good one to start off with. And if we look at the structure of a hydrogen atom, it has different energy levels. And so we have a ground state, which turns out to be 13.6 electron volts below where essentially the electron is no longer part of the hydrogen atom. But the first level, the n equal 2 level, is here 10.2 eV above that ground state. So let's just imagine we have a photon.
Now you'd imagine that most of this gas in space is going to be with electrons in the ground state, because remember the universe is cooling down. When it was very hot, at the time of the microwave background, the electrons would be up here. But as time goes on, they're going to dump down through the levels. And so pretty soon after the microwave background, most of the hydrogen should be cold enough that most electrons are going to be down here in the ground state.
So if you have a photon of, for example, 10.3 electron volts, it's going to come by and it's going to go right through the hydrogen atom because, of course, its energy is not quite tuned to the energy levels of the hydrogen atom. But if you have a 10.2 electron volt photon, so that's 121.6 nanometers, then when it sees the hydrogen atom, gets close to it, it can knock that electron up to the first level and excite the hydrogen atom.
So the photon has exactly the right energy to move the electron from here to here. One of the many weirdnesses of quantum mechanics is you might think one with a bit more energy would just move the electron from here to a little bit above that. But nope, in quantum mechanics, electrons have to have this energy, this energy. It can't have one in between. So that has exactly the same effect, that the photon has to have exactly the right energy. If it's too high or too low, no effect.
So let's think what happens if you have a universe full of hydrogen. And we know the universe has got lots of hydrogen in it. So if we look at a universe full of hydrogen, and for example, we have one of those 10.3 electron volt photons traveling through it, it'll just travel unhindered because there's nothing really to interact with. There's no hydrogen at the right, or the energy levels of hydrogen just aren't right.
I think you've forgotten something here. It might be 10.3 electron volts to begin with, but of course space is expanding. That means it's going to be losing energy.
Ah, that's right. So what we're really dealing with is a photon that is redshifting over time with its energy decreasing over time.
Here it goes, energy's going down close to 10.2. Oh. So while the energy remains above 10.2 electron volts, it can travel freely. The universe is transparent. But as it gets stretched, the wavelength gets longer, therefore the energy drops until it hits the magic value, and then it's in trouble. Suddenly the universe is opaque, and whichever hydrogen atom there's going to be, there's so much hydrogen around, it's always going to find one at the right place, you'd think. And you have an excited hydrogen atom and no more photon.
So pretty much any photon that is emitted blueward of 10.2 electron volts will eventually be redshifted and collide with the hydrogen atom and disappear. So let's look at some of those photons. And so, Paul, I'm just going to use one of your spectra of a quasar that has lots of UV photons. And if I put on here that magic place of 121.6 nanometers at 1216 angstroms, 10.2 eV, then we expect to have everything here absorbed.
Yes, what you can see is there's usually a big bump in the spectrum of quasars at this wavelength because you get electrons jumping down actually in the quasar, producing light at the same wavelength. This is called the Lyman alpha line. But you'd expect any photon down here at shorter wavelengths and hence higher energies. It could be emitted fine. It can fly through space a bit, but sooner or later it's going to get stretched enough until it matches 10.2 electron volts and gets mopped up. But you can see we are definitely picking up real photons at shorter wavelengths, higher energies. Somehow they're getting through.
So that is a question I guess we need to answer. Let's look at a higher redshift quasar. This one's at a redshift of, on average, about 1 or something, or even
About
less?
2, yeah.
About 2?
It's about 10 billion light years away.
Okay, so a long ways away. But let's look a little further, and we see something happens, that the quasar looks a little different in this case. So in this place, this is the magic wavelength of 10.2 eV, and here we see the spectrum is all chopped up, but it's kind of funny.
You would expect all the photons at this side, they can just escape freely because they're already longer, they've already got too little energy, and they'll just get even less energy as they go on. Down here, you'd expect there to be trouble. You'd expect nothing down here. You'd expect just a cliff and no flux down here. That was actually originally predicted by two people called Gunn and Peterson, Bruce Peterson being one of our colleagues here at Mount Stromlo many years ago. But instead, you don't see a cliff. You see instead, it looks like this has been attacked by termites or something. There is quasar light down here, but it's been bitten in lots of different places, like tooth marks all the way up and down it. So it looks like we're not seeing hydrogen filling space. But we've pretty much got to see hydrogen filling space. There's no way you can clear out all the hydrogen in intergalactic space. You don't need very many atoms. You know, one per several cubic meters is quite enough to mop up the stuff. But it seems like we are seeing absorption but only particular wavelengths. And somehow this gas has formed clumps, and either there's no gas in between, which is implausible, or for some reason the gas in between the clumps is not causing absorption.
So there's one way we can get rid of that, is if the hydrogen isn't neutral, if the hydrogen is ionized, the electron is separated from the proton, then one could imagine we could at least not have all of the light absorbed. So that would mean all these hydrogen atoms weren't hydrogen atoms, they'd actually be protons. And so our photon would just travel freely through the universe if only the universe was ionized. And that Lyman alpha forest, that termite-infested quasar, well, then we could understand that if the universe has some hydrogen in it, but let's say they're in little clumps, wherever the path between the quasar and us is free for a given wavelength, then we will see that light get all the way through. But for some places, the photons hit at a given wavelength, a hunk of hydrogen, and voila, they're gone.
So what we need is to take 95% or so of the gas and ionize it, strip the electrons off. And we'll leave about 5% in the form of neutral clumps, which can then cause absorption in all these termite holes over here. But that's kind of weird, because we've just said we started off with the universe that's ionized and very hot, and it cools down and becomes neutral. And we talked about that at length, because that's when the microwave background becomes free. And after that time, it just get cooler and cooler still. But somehow we've got to get it in reverse. So temperature starts off very high, gets colder, 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 and then for 95% of the gas has to come back up again.
Right, and it seems to be changing over time, because if we look at a really nearby quasar, so this is 3C273, the first quasar discovered, or at least identified, it only has a few little clumps of hydrogen. So the universe is changing, and that, I guess, isn't surprising because the universe is expanding, becoming less dense, but it seems as though something has happened. So the big question is, how would we change the universe and make it go from being neutral right after the cosmic microwave background to being ionized again? And so one could imagine heating it up, and as Paul said, that doesn't make sense, because how are you going to heat the universe up? It's cooling down. And I think the best way to think about it maybe is to look back at that hydrogen atom again and realize that if we have a really energetic photon, one that has more than 3.6 electrons of energy, if such a photon were to come into the hydrogen atom, it really will take that electron and throw it out of the system if it's absorbed.
Yes, so this is a more economical way. We're not heating the entire universe up. We just need a very small fraction of the power that we need to heat the whole universe up, which we certainly haven't got. But that power has to be in the form of ultraviolet photons. And these are pretty hard ultraviolet. This is much worse than the ultraviolet that gives you sunburn. This is 3 or 4 times more than the energy of that.
Right, so these are photons that are less than 91.2 nanometers. So those are, as you say, light that can never even reach the ground. But where would you go through and find such photons? Well, stars are the obvious things. So let's look at the spectrum of the sun. And if I put here where those ionizing photons are, we see a problem.
The sun produces lots of visible light. We know that. That's why our eyes see visible light. It produces some of what we call ultraviolet that gives us sunburn down here, but absolutely no ultraviolet right down at the energies we want, the hard ultraviolet down here. So the sun basically can't ionize anything.
So let's take a UV picture of a nearby galaxy which we can see well, and that's the Large Magellanic Cloud, and see where the ultraviolet's really coming from. And if we overlay a picture taken by the SWIFT satellite of the ultraviolet, we see there is a lot of ultraviolet coming out, and it turns out to be lined up on all the big, massive stars that are really hot and really bright. And so if we were to plot how bright stars are as a function of how massive they are, you get a diagram that looks like this. We see that as stars become heavier, they become much brighter, so this is how bright they are in solar luminosities, and they also become hotter. And hotter things put out more ultraviolet. And so there is a place, starting at about 10 times the mass of the sun, where stars produce lots of photons that have enough energy. So we need a universe that would appear full of really big, hot stars.